In the last episode, we explored the different types of GPR systems: impulse, continuous wave, multi-channel arrays, and even drone GPR. But now, no matter how advanced your radar is, what really determines the quality of your results is how you collect the data. In this episode, we'll look at field techniques, how to plan and execute a GPR survey so the data you bring home actually tells the story you need. We'll talk about why random surveys rarely work, what collection really means, and how to use GPS guidance, and why dense, carefully spaced lines are the key to finding hidden structures and utilities underground. So let's start with one of the most common beginner mistakes: the random walk survey. This usually happens when somebody rolls out a GPR cart across the ground in a few directions, stopping every time they see a strong hyperbola on the screen. They drop a flag or make a mark and think they've mapped the underground utilities. The problem is, GPR doesn't see everything all at once. It sees a narrow slice, a single cross-section directly beneath the antenna. Now, hyperbolas, those arch-shaped reflections you see on a radargram, they only appear when the antenna crosses directly over a buried object. If you miss the line by even half a meter, the reflection could look weak or flat or even invisible. So, in a random survey, you'll find the obvious high contrast targets like large pipes and rebar, but what you'll completely miss are smaller or deeper pipes that only show up when viewed in context of nearby data. That's why professionals don't do random lines. They collect data in structured grids, even like evenly spaced grid lines that can be later combined into a 3D volume or a series of horizontal slices. Imagine each radar line you record as like a vertical curtain through the ground. When you collect many parallel curtains, you can digitally slice through them at different depths. Now, these slices, also called time slices or amplitude maps, show the strength of the radar reflections at consistent depths or travel time. So we say like, here's a slice at 1 meter and it covers the entire area. You can think of them like aerial photographs of what's underground, one slice for each depth interval. Subtle features like small pipes, soil disturbances that might indicate pipes were there or are still there, rebar grids that just don't stand out clearly in a single radargram, they pop out on time slices. But when they're viewed as part of the full pattern, that's when the details emerge. Faint reflections repeated across several lines become a visible line or shape in plan view. This is why line spacing is so crucial. If the lines are too far apart, small objects fall between them and never appear in slices. So, as a rule of thumb, for high frequency antennas, let's say 1 gigahertz, used in concrete or shallow work, you need to have line spacing of like 10 centimeters. For mid-range antennas, say around 400 to 500 megahertz, a spacing of 25 centimeters is typical. And for lower frequency, say 50 centimeters will give you usable results. As a general rule of thumb, I like to think of the radar antenna itself as a lawnmower. And just like we would mow a lawn, we would take the lawnmower and go back and forth and go edge to edge, not of the wheels, but of the actual blade, of the actual radar antenna in our size. So the width of the antenna is a good guideline of the line spacing you should be aiming for full 3D coverage. Again, the higher the frequency, smaller the antenna, the finer the detail, and the closer your survey lines must be. Okay, I get it. Of course, collecting that much data takes time, but the payoff is tremendous. You can visualize the subsurface in 3D and detect subtle features you'll never see from a single line. One of the simplest tricks of improving your data quality is to cross expected targets at right angles. That's another thing. Why? Because GPR detects objects by the reflection produces when a pulse crosses a boundary. So if you cross a pipe or cable at the right angle, you'll get a clean, symmetric hyperbola, the perfect textbook shape that clearly shows the target's depth and position. But if you cross it obliquely, say, I don't know, at a shallow 30-degree angle, the hyperbola stretches out and may appear as a long, slanted blur or even a horizontal line, making depth estimates completely unreliable. So, whenever possible, plan your grids so that your survey lines cross utilities, rebar, and expected structures at about 90 degrees. This is one reason why archaeologists and utility locators often collect perpendicular grids, one north-south or one east-west, right, in 90 degrees. The second grid catches all the utilities that are parallel to the first grid, and it confirms what's seen in the first grid to help distinguish real targets from noise or linear interference. Let's walk through how to set up a grid and collect data in the field. A basic grid starts with two baselines, one defining your x-axis and one defining your y-axis. Lay them out with tape measures, survey tapes, or laser rangefinders, or whatever people use today. If the area is small enough, you can mark out line positions directly with chalk lines or spray paint or pin flags, spaced at regular intervals. Say whatever you're doing at 25 centimeters or 50 centimeters. You've got a grid, the outline of the grid. You can then collect data in a zigzag mode where you collect forward and then back on new files each line. Now this saves a lot of time, but it can introduce small positioning errors if the radar direction isn't carefully tracked. For maximum precision, I always, and many professionals do, prefer to collect unidirectional base. So always coming back to the same baseline and always walking in the same direction. It takes much longer to do, but it keeps the data orientation consistent and simplifies later processing. So what about obstructions? Well, real-world sites are rarely perfect rectangles, right? You'll encounter trees and fences and fire hydrants and parked vehicles. When this happens, simply leave a gap in your grid, note the obstruction's position, and resume the pattern on the other side. The software can interpolate around the missing areas later, but accurate notes are vital. If you skip a line or screw up the spacing or the direction, record it in your field log or project tablet immediately. For each grid, record the line spacing, the direction, the date, and any anomalies in the surface conditions. These details matter later when interpreting differences in reflection strengths or seeing a manhole cover that you weren't aware was there. Take a photograph. Most GPR software can now import photographs and georeference them into your project plan. So let's talk again about the big picture, data density. GPR is fundamentally a sampling tool. You're collecting a thin knife slice of information across a continuous underground world, and a very complex one. The more slices you can collect, the more complete your picture becomes. Sparse data, say widely spaced lines or a small sampled area, can easily miss crucial features. A pipe running diagonally across your grid might only appear on one or two lines or go completely unnoticed. Dense data with close line spacing lets software interpolate between traces to create a smooth, detailed slice. It also helps you spot these subtle patterns like soil layering and voids and disturbed ground that simply aren't visible easily on individual profiles. The rule of thumb: never collect less data than you think you need. You can always get rid of it, you can always delete it, but you can't go back and fill in missing gaps without another day in the field. So, look, if you can afford them, then a multi-channel array system are the ultimate solution. They automatically collect many parallel lines at once, producing incredible data density coverage that can be sliced in 3 dimensions. You'll see everything. But even with a single antenna, you can achieve similar quality results through careful, methodical gridding. Now, today, many modern GPR systems include built-in or external GPS antennas to track antenna positions automatically. Now, this is really useful for large or irregular sites where laying out a physical grid just isn't practical. Highways or open fields or archaeological landscapes. Instead of measuring every line, you simply walk the site and the GPS logs your path. The software reconstructs the grid afterwards based on the position of your data. Now, that sounds perfect. So much easier, right? Almost. There's a hidden issue called GPS latency, a time delay between when the radar records a trace and when the GPS logs the antenna position. And if your GPS data lags by even a fraction of a second and you're walking like at a steady normal pace, then each radar trace and position can be offset by several centimeters, sometimes 30 centimeters. At typical walking speeds, like a 0.3-second delay translates to an error of about 30 centimeters, enough to misplace utilities or make slices look really strange. In fact, pipes end up looking wavy when you do back and forth surveys. So that's why calibration is crucial for your GPS. Before your main survey, do a short calibration run. Pass over a known target like a metal plate or, well, a manhole cover is ideal, several times in both directions. What I recommend is doing large figure eights, and in the middle of each figure eight, don't slow down. Make sure you don't slow down. Normal walking pace. Pass directly over a manhole cover. And what you do in the software then is you mark each time you pass that manhole cover, and you start applying time offsets in the software until your cluster of points comes down to one location. And you'll see that there's latency, and it could be up to 0.8 of a second, sometimes 0.3 of a second, but no matter how fancy your GPS is, there is latency. Check how your your GPS and radar peaks lined up, and make that correction, because it's very, very critical. Otherwise, your GPS projects are going to look very strange. And also remember that GPS accuracy varies. Consumer-grade GPSs may have positioning errors of 3 meters or more, while survey-grade RTK receivers can, achieve centimeter and sometimes millimeter position. So for high-resolution utility mapping or archaeological work, RTK, or total station positioning, is the gold standard. For larger scale reconnaissance surveys, standard GPS is generally okay, but always document its accuracy. To summarize, GPR data collection is as much about discipline as it is about technology. Random surveys can find a few big hyperbolas, but they will miss most of the subtle patterns that tell the real story. Structured grids, close spacing, and perpendicular passes reveal those hidden connections. Slices let you peel away the ground layer by layer, showing patterns and shapes invisible in single lines. Tight spacing, especially for high-frequency antennas, is the difference between noise and a very clear image. Laying out grids carefully, making and marking baselines, and keeping accurate notes ensure your data can be interpreted confidently later. Handling obstructions, maintaining orientation, and collecting consistent metadata is all part of being a good GPR operator. And finally, whether you use a tape measure or GPS position, accuracy is everything. If your radar doesn't know exactly where each trace was collected, no matter how much cool post-processing you do, it won't make up for that original error. So, before your next survey, plan your grids, mark your baselines, and think about your spacing. GPR is a powerful window into the subsurface, but only if you collect data with precision and intent. In our next episode, we'll look at what happens after data collection, how we process GPR data to remove noise, correct distortions, and tease out meaningful reflections. Until then, remember, every clean radar image starts with careful fieldwork. If you take your time to plan, measure, and document, your radar will reward you with clarity, confidence, and insight into the world beneath our feet. Thank you so much. See you next time.